next chapter deals with the reactions of alcohols, where in the last chapter we saw reactions that make alcohols. So we're going to learn reactions that involve the OH group here. So let's talk about some prerequisite definitions. So oxidation, we talked about that a little in the last chapter. It's the loss of hydrogen and the gaining of a bond to a heteroatom, such as nitrogen or oxygen. So we're going to look at oxidation of alcohols, so it's going to be the oxygen there. And reduction is the gain of H2 or H minus, right, and the loss of a bond to a heteroatom. So the opposite of what we saw up above. So there are cases where neither oxidation or reduction occurs. So examples of that would be addition or loss of H plus, HX, H2O. All right, so let's look at our first reaction. Let's just jump right into oxidations. We're going to look at that on the first 3 or so pages here. So there's a couple reagents that can be used, and some of these just show up over and over again, and Jones reagent is one of those. So it's the oxidation to carboxylic acids using Na2Cr2O7. So that's sodium dichromate in the presence of acid. So we call that sometimes acidified sodium dichromate. If you look down below, let's follow this reaction. So down here, we have a primary alcohol, and the way that we're going to see the reagent often is Na2Cr2O7, H2SO4. We'll see down below that there's other versions of this thing. So here's Na2CrO4, chromium trioxide, right, dilute acid, or just Jones by itself. So students tend to like just to write Jones because there's less chemicals that are involved there. Now, this solution to start with over here is orange. So it has an orange color to it. So in the presence of this alcohol, that alcohol gets oxidized over here to form an aldehyde. And because that aldehyde still has an H atom that's on it, it can get further oxidized. So the reaction cannot be stopped here. It's important to note that. Cannot stop reaction here. So it just continues. This is just to show you kind of like your stepping stone, your halfway point. So we still see the sodium dichromate, sulfuric acid in there, and now we get oxidized to the carboxylic acid. So primary alcohol becomes aldehyde, aldehyde becomes carboxylic acid. And then side note, the other thing that we get is we get this fellow here. Notice the oxidation state of chromium has changed, and this is a green color. So sometimes we can use this, if you look down below here, sometimes we can use this as a qualitative test to determine whether or not we have an alcohol. Right? So you take a little bit of alcohol in a test tube, put some Jones in, and see if the Jones turns from orange to a green color. Now, what if you wanted to stop at the aldehyde? Well, if you want to stop at the aldehyde, then you need to use something that's not as powerful of an oxidizer as the chromic acid solution, the Jones solution. So the weaker version of this is called PCC, or pyridinium chlorochromate. So same idea down here. Here you have a primary alcohol. That's what your starting point is, right? And in the presence of PCC, this gets oxidized and stops, this is the important thing, it stops at the aldehyde. So it's important to note that this reaction stops here. That's important. So we're going to see these reactions a lot as we go through this chapter, and they come back in next semester too, because we have a couple chapters that deal with aldehydes and ketones. So PCC would be used for that, and then we have a couple chapters that deal with carboxylic acids. So we see Jones popping up there. Okay, so let's look at one little detail of this reaction. I always like to talk to students about this. because it's just interesting, and we don't get a chance to see how metals are involved in reactions very often. So what I want you guys to see and understand is the oxidation of secondary alcohols to form ketones. Okay, so we're not going to worry about that primary alcohol oxidation that we saw before with PCC. We're not going to learn the mechanism of that. We're not going to learn the mechanism of oxidation of primary alcohols using Jones, but secondary alcohols I want us to be familiar with. So this oxidation, when we look at this observed reaction, that could use Jones. Right? Jones would do this, or if we really wanted to, we could use PCC. And what I want to look at with you guys down below is this Jones. Now remember before I said Jones can be written a lot of different ways. Your textbook tends to write Na2Cr2O7/H2SO4, right? The other version of this is to write this as H2CrO4. It's a chromic acid. That's what I want to look at down below as our reactant. So let's take a look down here below and see if we can make a little bit of sense about what's going on here. A little bit of an involved reaction, but we'll make it work out here. So let's take here chromic acid. So take a second and follow me here on drawing out chromic acid. So I'll give you a second to catch up. Now chromic acid is in the presence of H3O plus. It's a strong acid, right? So what we have here is HOH plus in solution. So the first thing that we do is we're gonna activate essentially one end of this molecule by grabbing a hold of an H atom. So we're gonna do this. So what that gives us is this intermediate where we have an H connected to an oxygen. And then the chromium part is all just the same, right? So just collapse that stuff down a little bit. And then we have a plus charge there, right? Okay, so now this is what we're going to use as our reactant. And I'll take here something like isopropyl alcohol, right? 2-propanol. What happens here is that this is our nucleophile, and it's going to come around and grab a hold of the chromium, and then we're going to lose water. So water's a good leaving group, right? All right, so let's see what we get here. I'm going to swing that around a little bit, so we're going to draw it like this. So here's our carbon, right? That's the carbon of our isopropyl. That's connected to an oxygen, right? That oxygen's connected to an H, and now it's connected to the chromium part, right? So chromium, same deal down below, all of its jewelry and all of that other stuff, okay? All right, so we get this next intermediate. So the only thing that we're missing here is we need to put an H atom right there, right? So we got an H that's there. Okay, so what we want to do next is we want to take care of this hydrogen here. So just to show you up above, that H that I circled there is this H that's right there. So we need to lose that H. So water's going to come around here and grab that H, and we're going to do this. So then let's draw this thing out again. So here we have a CH3 carbon. I'm just going to move this down a little bit and draw it a little bit more square. And then an O, and then the chromium with the rest of its luggage. So we just lost one of the H's. And if you look up above, that green H was lost. Now we need to take this H. We need to lose that guy. That is this guy right down here. So let's take a look and see exactly how that happens. So let's continue on here. We're going to use water to do this again. So H2O. Now water is going to come around, grab that H, So these electrons now need to come down right here. They're going to do that. And then we're going to come down and push electrons back onto the chromium. So in addition to H3O+, we're going to get our CH3, carbon, CH3. Right? This guy right here is now going to have our double bond. So double bond O. And then we have this remaining fellow over here. Right? So plus our chromium here, double bond O, right? OH here. And then the oxygen down here actually is going to have a shift in electrons. So we're going to come over here and we're going to add one more arrow just to finish that, right? And take care of this guy. So then you get a negative charge right there. Right, and then I'll just do this dot, dot, dot. That eventually becomes chromium 4. Right? So again, that's the oxidation step of this reaction, or demonstration of this using a secondary alcohol. Now, if we look at a tertiary alcohol down here below, easiest reaction of them all. So let's take a look at it real quickly. And let's see what can happen here. So let's draw out CH3, CH3, OH, CH3, and then can we oxidize this? So sometimes we'll just do brackets like that. Can this be oxidized? Well, there's an H here to be lost, but there's no H on that carbon atom. So simply put, tertiary alcohols cannot be further oxidized. Right? Otherwise, you'd draw something like this if you tried to do it. Right? So you lose that H. So this cannot occur. Right? That should make you feel kind of nauseated. Now, looking at all this stuff together, we can summarize the last couple pages here by this little table. So we see Jones reagent, right? So Jones reagent can be kind of spoon-fed to you 3 different ways. They make primary alcohols become carboxylic acids, secondaries become ketones. PCC has a common name here too called the Collins reagent. It takes primary alcohols and oxidizes them to aldehydes, secondary to ketone. And then the other thing that we see sometimes, and we don't get into it much in some semesters, and this is going to be one of those semesters, but you might see this pop up from time to time, is potassium permanganate can oxidize alcohols to carboxylic acids or to ketones. So those are the 2 types of oxidations that we're going to see. In the next section, I'd like to talk to you guys about biological oxidation. So we'll see you next time.